Welcome back. Now we're going to discuss the second derivative test for local extreme values for multivariable functions. So what this says is, suppose we have this function and both its first and second partial derivatives are continuous throughout this disk space centered at AB. And if we find the first partial with respect to x and the first partial with respect to y, and then determine this AB value, this critical point where they're equal to 0. Well, what we can do is we can determine if the function has a local max, a local min, or a saddle point, or we could even have an inconclusive test based off of some of our second partial derivative findings. Now, I know this looks like a lot of jumble here, but I want to point out that we have this fxx, fyy, minus fxy squared showing up. So it looks kind of jumbly, but it really just represents a value which we can call the discriminant, d. So d is equal to the second partial xx times the second partial yy minus second partial xy squared. This is called either the discriminant or the Hessian. Another way we can remember this formula is sometimes easier for students to remember. fxx, fxy, fxy, fyy. And if we think about that as being a discriminant, we would multiply and then multiply, subtract that second value or second product. So all those underlined orange things, we are considering this discriminant. Either the discriminant is positive, greater than 0, that discriminant is negative, or the discriminant is equal to 0. So if we have a positive discriminant, if the second partial of the function with respect to x twice, if that is a negative value, that's a local max. And if that same second partial derivative is a positive value, then it's a local min. And that should convey a little bit to our second derivative test for extreme values from Calc 1, where if the second derivative was negative, it represents a max. And if the second derivative is positive, it represents a min. In this situation, though, that discriminant value must be positive. And in the event the discriminant is not positive, then we might have a negative value or we might have a 0 value. If the discriminant is negative, that means this critical point actually would represent a saddle point. And if the discriminant equals 0, the test is inconclusive. And in this case, we have to find another way to determine the behavior of the function at this AB critical point. So if I were to write this a little bit more briefly, if we think about a table, the discriminant defined as above, still here on the screen, and we think about fxx. If the discriminant is positive and that function value, when you evaluate that second partial derivative of x with respect to x twice, if that's negative, conclusion would be that we would have a local max. And if the discriminant is positive and that second partial is also positive, that would mean we would have a min. If the discriminant is negative, doesn't matter what this is, we know we have a saddle point. And if the discriminant is equal to 0, it's inconclusive. So that's just kind of a different way of writing it to maybe help you think about what we're going on or what is going on and what we are considering when we are trying to determine whether or not these critical points represent a local max, a local min, or a saddle point. So let's do an example. In this example, we need to find the local extreme values, and we need to be able to state whether or not they represent maximums or maxima or minima. I should pluralize that correctly. So my function f of xy is equal to xy minus x squared minus y squared minus 2x minus 2y plus 4. All right, so the first thing we're going to do is find that partial derivative with respect to x. So that means we treat y as a constant, and I will get y minus 2x plus 0 minus 2 plus 0 plus 0. And then my partial derivative with respect to y, that means I treat x as a constant. I've got x plus 0 minus 2y plus 0 minus 2 plus 0. So what we do now is we set up a system. I'm going to set each of these partials equal to 0. And we need to solve for the xy values. Now, when I think about solving a system, notice I've got both of these minus 2's. I can add them each to the right side of each equation. So I'm going to do that with my eraser here. I'm just going to say equals positive 2 equals positive 2. Now I can use either the substitution or the elimination method to solve this system. I can very easily say that x equals 2 plus 2y. Then taking that top equation, y minus 2x equals 2, I can plug that in for x. So y minus 2 times 2 plus 2y equals 2. Y minus 4y equals 2. I've got negative 3y, add that 4, gives me 6. And we determine that y is negative 2. Now, if y is negative 2, I can find my x value, because x equals 2 plus 2 times that y value we just found, negative 2. And simplifying that, I'll get that x equals 2 minus 4, or negative 2. So we have one critical point here. So my critical point is the ordered pair negative 2, negative 2. And that represents my A and my B values in my definitions. So this is where an extreme value may occur. Of course, we need to use our second derivative test in order to determine if this is a local max, a local min, or a saddle point. And of course, remember that that second derivative test could also be inconclusive. So let me clean my screen up. So now what we need to do is we need to find the second derivatives. So I'll do that here. We've got fxx, that's going to be negative 2. fxy is going to be 1. And fyy is going to be negative 2. Using this, I'm going to determine my discriminant. And the value for my discriminant is fxx times fyy minus fxy squared. Or rather, in this situation, we have negative 2 times negative 2 minus 1 squared. That simplifies to 4 minus 1, which is 3. So since my discriminant is a positive number, it's greater than 0, then we know that this is going to be an extreme value. It's either a local max or a local min. So then we go back and we look at fxx, the second partial derivative with respect to x twice of our function. In this situation, that is a negative value. We have -2. Since that is less than 0 and the discriminant is positive, we can go and say that this is a local max. And the local max for this function occurs at the point -2, -2. So that is where the local maximum occurs. So we'll say local max occurs at -2, -2. And if I wanted to know what that local maximum value was, we plug it back into the original function and we'll get +8. So this is where the local max is, and this is what the local maximum value is.